What is the difference between Float32, Float16, and BFloat16? In the world of AI, choosing the right format can be the difference between a successful training session and a complete system failure. To understand why these formats matter, let's look at a problem every developer needs to know. The dreaded CUDA out-of-memory error. This nightmare happens when your model exceeds your GPU's capacity. But why does it happen, and how can these different float formats save your memory? To find out, we need to dive into the bits. To understand why different float formats matter, we first need to look at the IEEE 754 standard. This is the universal language computers use to store and calculate decimal numbers. Every floating point number is broken into three distinct parts. First, the sign bit. This is a single bit that determines whether the number is positive or negative. Next, we have the exponential part. Think of this as the scale of the number. The more bits we dedicate to the exponent, the larger the range of numbers we can represent, from the incredibly small to the astronomically large. Then comes the mantissa, also known as the fraction. This part determines the precision. It stores the actual significant digits of your number. The longer the mantissa, the more detail and accuracy you have after the decimal point. In a standard Float32, these 32 bits are distributed like this: 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa. This balance provides a great mix of range and precision, but as we'll see, it's not always the most efficient choice for AI. Let's put the theory into practice. We want to see how a computer actually stores a specific number, in this case, 98,304. Here is what that looks like in a 32-bit sequence. First, we look at the sign bit. Since it is 0, we know immediately that our number is positive. Next, let's decode the mantissa. By calculating the fractional bits, we find that this sequence represents the value 1.5. This gives us the core digits of our value. Now, for the exponent. The binary string 10001111 translates to 143 in decimal. In the Float32 standard, we subtract a bias of 127, leaving us with a true exponent of 16. When we put it all together, we multiply our mantissa of 1.5 by 2 to the power of 16. The final result is exactly 98,304. It fits perfectly in 32 bits, but as we're about to see, things get complicated when we try to shrink this down to save memory. Now, let's try to save memory by switching to Float16, also known as half precision. In this format, we only have 16 bits to work with. We still use 1 bit for the sign, but the distribution changes drastically. We only have 5 bits for the exponent and 10 bits for the mantissa. So, what is the largest possible number we can write with only 5 exponent bits? By using the highest available exponent value and filling the mantissa with ones, we reach a maximum limit of exactly 65,504. You might wonder, why not set all the exponent bits to 1? According to the standard, an exponent of all ones is reserved to represent infinity. It cannot be used for actual numbers. This is our problem. Our target number, 98,304, is much larger than the Float16 limit of 65,504. If we try to use Float16, our value overflows and becomes infinity, leading directly to those CUDA out-of-memory or NaN errors we saw earlier. So, we are stuck. We need to save memory by using only 16 bits, but our target number, 98,304, is too large for the standard half-precision format. How can we possibly fit this value into a 16-bit space? The answer lies in a clever architectural trade-off: increase the exponent and decrease the mantissa. By dedicating more bits to the exponent, we can match the massive range of a 32-bit float, even if it means sacrificing some fine-grained precision in the mantissa. This specific balance is the secret sauce behind BFloat16, the format that powers modern large language models. Let's see exactly how those bits are distributed. Introducing BFloat16, or brain floating point. To solve our memory problem without losing range, we've completely redesigned the 16-bit structure. We still use 1 bit for the sign, but here is the game changer: we've increased the exponential part to 8 bits. By using 8 bits for the exponent, BFloat16 matches the exact same scale or range as the original 32-bit float we started with. To make room for this in a 16-bit space, we've reduced the Mantissa to just 7 bits. Let's look at the result. When we write our target number, 98,304, in this new format, the binary string becomes 010001111110000000. Because we have those 8 exponent bits, we are no longer trapped by the 65,504 limit of standard Float16. The calculation is successful. We have represented 98,304 perfectly using only half the memory of a Float32. This is exactly why BFloat16 is the standard for training massive AI models. It gives you the range of a heavyweight format with the efficiency of a lightweight one. Let's see this in action using PyTorch. We define our target value as 98,304. When we store it in a standard Float32 tensor, it works perfectly. But look what happens with Float16, because our number exceeds its 65,504 limit. The result is INF, a total overflow. However, even though BFloat16 uses the same 16 bits, its expanded exponent handles the number with ease. Success! Now, why not just stay with Float32? The answer is memory efficiency. By checking the element size of our tensors, we see that Float32 consumes 4 bytes per value. In contrast, both Float16 and BFloat16 use only 2 bytes. By switching to BFloat16, you effectively cut your model's memory footprint in half without losing the ability to represent large numbers. To wrap up, let's look at the absolute limits of these formats. Here is the proof of what we've discussed. Float16 hits a hard wall at exactly 65,504. Meanwhile, BFloat16 boasts a massive maximum value of approximately matching the range of Float32. This unique balance makes BFloat16 the ultimate tool for modern AI engineering. Next time you're training a model or facing an out-of-memory error, remember that it's all about how you manage your bits. If you found this deep dive helpful, don't forget to like and subscribe for more AI engineering insights. Thanks for watching.